My name is Flash Isaac, and I'm a teacher from the future. When I was much younger, I saw thousands and thousands of people fail Jamb and unable to gain admission. This made me travel in time. Now I am back with the Flashlearners Jamb app and a series on YouTube tagged 120 Days to Jamb. My mission is to help you blast Jamb and as well get justice for everyone who Jamb has served breakfast. This is episode number 34 of the 120 Days to Jamb Physics with Flash Isaac. In this episode, we shall be looking at quantity of heat, or you can say heat energy. We have been able to establish that energy is the ability or the capacity to do work. And we're also able to establish that heat is a form of energy. And this form of energy only occurs or appears when there is difference in temperature. If you have object A and object A, once these objects are at different temperature, a form of energy that flows is called heat energy. This is why you see that heat will naturally flow from hotter objects to cooler objects, because there is difference in temperature between the objects. And we also agree that temperature is the measure of the movement of molecules. Temperature is the measure or is the average kinetic energy that molecules possess. If the molecules possess so much energy and they move at a very fast rate, we therefore say that the temperature is very, very high. Before I embark on my procedures, let's look at the three theories of heat. The first one is the motion theory. The second is the caloric theory. And the third is the modern view of heat. The modern view of heat or of heat energy combines the motion theory and the caloric theory. The motion theory, it says that heat is a form of energy produced when objects are set in vibration or they are in motion. When object molecules are in motion or in vibration, the energy produced is referred to as heat energy. Meanwhile, the caloric theory states that heat is a weightless fluid called caloric fluid with balanced forces, which means the resultant force of heat energy is zero. The force acting on either side balances each other. While the modern view combines both the motion theory and the caloric theory of heat. Now, how does this change the price of Gari in the market? We've looked at the rival theories of heat, which are the motion theory and the caloric theory. Motion theory states that heat is produced when substances are set in motion or in vibration, when substances move as a result of vibration, which means the motion theory speaks of distance, since motion is change in position of objects with time. Meanwhile, the caloric theory, which says that motion is a weightless fluid or caloric fluid that contains unbalanced forces. Motion theory states that there is distance, caloric theory states that there is a force. And the modern view of heat combines the two, which states that heat is equals force times distance. Now, force times distance is energy. This takes us to the sources of energy. What are the various places, forms we can get this heat energy or heat generally? The sources of heat can be classified into renewable source and non-renewable source. Renewable sources of heat are those sources that can be reused. They keep coming, you don't use them up. Once you use, you reuse, you can recycle. But the non-renewable sources of heat, they are used up once. You cannot reuse them, you cannot renew them. The examples of renewable source of heat are water, sun, wind, and biogas. While the non-renewable sources of heat are diesel. Once you use diesel, it's gone. You buy another one, you use, it's gone. Petrol, kerosene, natural gas, coal, charcoal, and wood. All these are non-renewable sources of heat. Now, if you look at biogas, wind, and sun, to an extent, you agree that, okay, this is a source of heat. I know there is a question in your mind. How is water a source of heat? To get heat from water, we use the water source heat pump. Water source heat pumps. When they come in contact with any water body, they extract that heat energy or heat from water and convert into other usable forms of energy. Now, there are ways we can convert other form of energy to heat energy. We can as well convert heat energy or heat to other form of energy. Now look at this number 1 to 4. We can use these methods to get heat. These are the ways we can get heat energy. For example, the electric kettle or heater will convert electric energy to heat energy. At source, we are able to generate heat from electric kettle. Falling objects will convert potential energy to heat energy. Remember, when you are at a height, the energy you possess is potential energy. Now, as that object falls, that potential energy will be converted to heat. And when water falls, water fall converts kinetic energy to heat energy. Then, coal fire or burning, all these, they will convert chemical energy to heat energy. We can also convert heat energy to other form of energy. For example, in thermocouple or thermopipe, heat energy is converted to electrical energy. In heat engines, heat energy is converted to mechanical energy. Which of the following converts heat energy to mechanical energy? The answer is heat engines. Now, we have two types of heat engines. We have two types of heat engines. They are the steam engine and the internal combustion engine. Ladies and gentlemen, if you can't see these things on the board very clear, like crystal clear, it means two things. Either you are watching a low quality version on YouTube. This video is uploaded in 1080p, and from my preview, they are very clear, even my view on YouTube. So what you do is, you click on that three small dots on YouTube, then you go to quality. From there, you can choose a higher quality, so you see me very well and you get a better experience. Most of you download these videos. When you download, most of these downloaders, they will give you the very low quality version. As such, you won't really get the best experience. So do all this, right? Let us proceed. There are two types of heat engines. They are the steam engine and the internal combustion engine, ICE. Steam engine and the internal combustion engines. Both of these guys are heat engines and they convert heat to mechanical energy. Now, this internal combustion engine, we have two types of them, or at this level, they are of two types. They are the petrol engine and the diesel engine. If you look at your devices, your machines, your generator, you see that some of the engines use petrol, while for some engines, you need to put diesel. These are the two types of internal combustion engine. When two bodies are at the same temperature, we say that these two bodies or objects are in thermal equilibrium. Do you know why? There is no heat flow between these two objects, because heat will only flow when objects or bodies or substances are at different temperature. when there is no net flow of heat between two objects, we therefore say that they are in thermal equilibrium. Now, let's go to the big boy. The big boy. Thermal heat. Thermal heat. We are now dealing with quantity of heat. And this quantity of heat, we can say visible heat, because we have another form of heat which is referred to as invisible heat. That one is referred to as latent heat. It is the heat that is available or present when there is change of state without change in temperature. We see an object can just change from solid to liquid, liquid to solid, without change in temperature. That is invisible heat or latent heat, and that should be our next topic. But for now, let's look at the visible heat or thermal heat or heat energy or quantity of heat. It is the heat required with a temperature difference but with no change of state. If I give you a solid, the heat required for this solid or applied to this solid while it still remains solid, that is thermal heat. The solid does not change, unlike latent heat. In fact, latent heat is the opposite of thermal heat, because latent heat is the heat required without a temperature difference but with change of state. They are opposite. In latent heat, temperature remains the same, no change in temperature, but the object or substance will change state, solid to liquid, liquid to gases, and wherever. Now, once again, thermal heat. It is the heat required with a temperature difference. Temperature changes, but there is no change of state. The substance in question does not change state. If it were solid, it will remain solid. Liquid, it will remain liquid. There is no change of state of matter. Now, it is also the energy required to change the average position of molecules. Of course, once there is a difference in temperature, the molecules will move. That is so true, and they also refer to the same thing. Discussing thermal heat, we have latent heat capacity and specific heat capacity. We have heat capacity and specific heat capacity. But before then, thermal heat is H is mc theta. mc theta. mc theta. Now, the C here, as we can see here, is specific heat capacity, which means if we make this C subject formula, it will be the thermal heat over mass times temperature. So, C is specific heat capacity and it is thermal heat divided by mass times temperature. On the other hand, mass times specific heat capacity is heat capacity, which means heat capacity is mc and this is equals thermal heat divided by temperature. This takes us to the differences, the dichotomy, the disparity between heat capacity and specific heat capacity. And this is the part that a lot of students confused. Now look at it. If this is a block, the heat required to change the temperature of this block by 1 degree Celsius or 1 Kelvin is referred to as heat capacity. We don't care the mass of the block. So long this overall block, you are able to change the temperature by 1 degree Celsius or 1 Kelvin, that heat that you applied is heat capacity, which means heat capacity is the heat required to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. Now look at something else. If this is another block and we have something like this, And we say that this block is 6 grams, meaning here is 1 gram, 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 and here is 1 gram. And this is the entire block. The quantity of heat that you need to raise the temperature of 1 gram of this substance by 1 degree Celsius or 1 Kelvin is referred to as specific heat capacity. When we say a unit mass, it means 1 grams. 1 unit is 1 grams. So this block now, specific heat capacity will be concerned with the heat you will need to raise the temperature of 1 gram of heat by 1 degree Celsius or 1 Kelvin. Which means here specific capacity, here specific capacity, here specific heat capacity. But heat capacity is not concerned about a particular mass or part of the substance or object. It is concerned about the heat you need to raise the temperature of the entire object by 1 degree Celsius or 1 Kelvin. And once again, specific heat capacity is the heat required to raise the temperature of 1 grams or of a unit mass by 1 Kelvin or 1 degree Celsius. And these are ways of preventing heat losses. Before we look at that, there are 2 ways of finding specific heat capacity. We can determine specific heat capacity using 2 methods. One is the mixture method, and the second one is the electrical method. The mixture method works on the principle that heat lost by an object is equal to the heat gained by another object. If I have a hot object and I put another object inside, let's say a cooler object, the heat lost by the hotter object should be equal to the heat gained by the cooler object inserted. Of course, that is true because heat is basically moves from one form to another. If this is 100 degrees Celsius and this is 0 degrees Celsius and I place this here, removing this, I discover that this has become 50 degrees Celsius. What does that mean? This one has lost 50 degrees Celsius and this one has gained 50 degrees Celsius. So the heat lost by this guy is equal to the heat gained by this guy. Meanwhile, we have another method of determining or finding specific heat capacity. That is the electrical method. In electrical method, heat is supplied to a body or an object, and this object is placed in contact with what we call calorimeter. And this calorimeter is used to determine the heat capacity, specific heat capacity of the object. And to prevent heat losses, we lag the calorimeter. Lagging of calorimeter is placing an insulator inside the calorimeter, and this guy is used to measure specific heat capacity. Then to prevent heat losses using electrical method, you have to shield the calorimeter from drought. Make sure there is no drought, and polish the inner and outer surface of the calorimeter. Then you use an insulating lid. So all of these are enough introduction to quantity of heat or to heat capacity and specific heat capacity. Now let's begin to answer questions. From there, you will see what you're supposed to do under each question and how to go about questions under quantity of heat. I know you are going to fail this question, but here we go. The amount of heat required to raise the temperature of a body is dash. A. Thermal energy. B. Specific heat capacity. C. Heat capacity. And D. Latent heat. If you say latent heat, I know you won't say that. You are wrong. If you say specific heat capacity, you are wrong. If you say heat capacity. You are wrong. So the amount of heat required to raise the temperature of a body is thermal energy. You may be wondering, why is it not heat capacity and why is it not specific heat capacity? Remember what I wrote here. I told you that thermal energy is the amount of heat needed to raise the temperature of a body when there is temperature difference, but without change of state. And I further went to explain that we have heat capacity and specific heat capacity. Heat capacity is the heat required to raise the temperature of object by 1 degree Celsius. So the heat required to raise the temperature of 50 grams of copper by 1 degree Celsius is heat capacity. So when you hear temperature, you know that it is heat capacity. Now when you hear or you see temperature and mass, unit mass by 1 degrees, then you are talking about specific heat capacity. Here, they did not mention mass, they did not mention temperature. So when you see a plain question like this, it is thermal energy. Take note of that. And the next question we have here is the quantity of heat needed. Ladies and gentlemen, we are making use of the Flashlearners Jamb application, and it is compulsory for you to install one for yourself. Very, very compulsory. The quantity of heat needed to raise the temperature of a body by 1 Kelvin is the body's heat capacity. They did not mention mass, they only mentioned temperature. So we are dealing with heat capacity, not specific heat capacity. Now let's go to calculations. For every calculation, you will see under heat capacity and specific heat capacity, it is basically conversion of energy from electrical to heat. Yes, that is what is under. That is electrical method of heat determination. Then under mixture method, once you are given two objects and they say that one loses heat, the heat lost by one is the same thing as the heat gained by the other one. Or you are taught that the same amount of heat is supplied to different bodies or objects. As such, you equate their thermal energy or their heat energy. It doesn't get difficult. There is no difficult question under heat capacity and specific heat capacity. Before now, we have been able to establish that H is equals mc theta. Actually, change in theta, which is temperature rise. When you hear temperature rise, it means difference in temperature. And we know that this is thermal energy. Or you can say heat energy or heat generally. Out of this formula, if you make C subject formula, you get H over m theta. So this C is specific heat capacity. Now when you make MC subject formula, you get thermal heat over temperature. MC is your specific heat capacity. No, MC is your heat capacity. So C is specific heat capacity, MC is heat capacity. When it comes to electrical energy, don't worry, we'll soon enter electricity and electrical energy and electrical power. There are various ways you can determine electrical energy or various formulas for electrical energy. Electrical. The first one is energy is IVT. Current times voltage times time. The second one is electrical energy is power times time. Power times time. Then electrical energy or energy loss or power dissipated, that is I square R. Then in terms of energy, it is I square ROT. With this formula, your life is set when it comes to heat energy, thermal energy or specific heat capacity. Now look at this question. A boiler of resistance 20 ohms is used to change the temperature of 2 grams of water from 15 degrees Celsius to 75 degrees Celsius. How long will it take the boiler if the supply current is 6 amp, taking specific heat capacity of water to be 4,200 joules per grams per Kelvin, joules per kilograms per Kelvin, which means the unit for specific heat capacity is joules per kilogram per Kelvin. Ladies and gentlemen, you already know we are given resistance of this boiler and we are given the temperature, we are given mass, we are even given current, and obviously we are converting thermal heat to electrical energy, or electrical energy rather to thermal heat. And for electrical, one out of these 3 formulas are what we need. Since here we have resistance and we have current, it basically means this is what we shall work with. So electrical energy is converted to heat energy, and electrical energy is I squared ROT, and this is equals heat energy remains MC change in theta. That is it, ladies and gentlemen. And we are looking for time. Anytime you hear how long, you are dealing with what? Time. When you hear how far, you are dealing with what? Distance. From here we have everything that we need. Current is 6 amp, so 6 squared times resistance is 20 ohms times time. Of course, this is what we are looking for. This is equals mass 2 kilogram times specific heat capacity 4,200 times change in theta. Change in theta is 75 degrees minus 15. That is change in temperature. 75 degrees Celsius minus 15 degrees Celsius. I think that should be 60 degrees Celsius. 6 squared times 20 times T is 720 T. 2 times 4,200 times 60, that is 504,000. To get time, we divide here by 720 and we divide here by 720. This divided by this is 1. So time is equals 700 seconds. Anytime you solve for time, the answer you get naturally is in seconds, because we convert to seconds before solving, which means this time is in seconds. But looking at the options, they gave us in minutes and seconds, and we know that this is 700 seconds. How do we convert to the given answer? To convert seconds to minutes, we divide by 60, and to convert seconds to hours, we divide by 3,200. That is 60 times 60. If we divide 700 by 60, you will get 11.6666667. You approximate, or you say 6667. Now this 11 is your hour, H-O-U-R, which means we have 11 hours. If you remove these 11 hours, you are left with 0.66667. To convert this other part to seconds, just multiply by 60. Once you multiply here by 60, you get 40. So the whole number is the hour. To get seconds from the other part of the decimal point, multiply by 60. That should give you 11 hours 40 seconds, as seen in option A. A block of aluminium is heated electrically by a 25 watt heater. If the temperature rises, by 10 degrees Celsius in 5 minutes, the heat capacity of the aluminium is. So, ladies and gentlemen, the time is far spent. Yes, time is far spent. I think with this, we shall come to the end of this episode. So you can look at the question I just read out, or relax for the next episode, which is already released. That is it. Make sure you get the Flashlearners Jamb app and play with questions. Subscribe to this channel and tell your friend about it. I know most of you prefer to be downloading videos, but if you find any video helpful, just go back to YouTube, like, comment and share so that others will actually see that the video makes a lot of sense. So see you in the next episode where we shall answer the question I just read and more questions under Tema Heat. Take care of yourself.